This is Software Engineering Radio, the podcast for professional developers, on the web at SE-Radio.net. SE-Radio brings you relevant and detailed discussions of software engineering topics at least once a month. SE-Radio is brought to you by IEEE Software Magazine, online at computer.org/software.
OpenStack is an open-source cloud operating system. John-Purrier is a founder of OpenStack and the CTO of Atomic Software. As Atomic's Chief Technology Officer, John is responsible for driving the organization's automation strategy. With more than 20 years of IT industry leadership experience, John was most recently CTO of CenturyLink Innovation Labs, focusing on new and emerging cloud technologies, including multi-cloud interoperability and DevOps. Previously, John was strategic and technology leader at AppFog, and he led the development and delivery of the first 3 releases of Microsoft Exchange Server. And he also led R&D for the Rackspace Cloud. John-Purrier is a founder and board member of OpenStack. John, welcome to Software Engineering Radio.
Well, thanks for having me, Jeff.
What is OpenStack?
Well, OpenStack is as you said, it's an open source project. It's a cloud operating system. Originally, the idea behind OpenStack was to create an open source infrastructure as a service platform. And, the original founders were Rackspace and NASA. And the 2 original projects were a compute project and a object storage project. Of course, since then, in the last 6 years, the numbers of projects and the scope of the projects has grown well beyond that original vision.
To level set for some of our listeners who may not know the term, what is infrastructure as a service?
So the way to think about infrastructure as a service is instead of going out and buying your own computers, finding a building, getting a lease, hooking up power and air conditioning and running a data center, you're essentially leasing that from somebody else, right? So while you can have projects that are private infrastructure as a service, when we talk about IaaS or infrastructure as a service, most people are referring to public clouds like Amazon, Azure, or Google Cloud, right? So the simple way of thinking about it is I'm essentially renting servers from somebody else.
So we have these public clouds like Amazon, Google, Microsoft Azure, for example. Why do we need an open source cloud operating system?
Well, that's a great question, and I guess the question could be, why do we need any open source versions of proprietary implementations? And I would argue that first of all, it's just good for the industry and the ecosystem, but in particular around cloud, cloud is very collaborative, right? It's a coming together of a lot of different companies and organizations, and the ability to collaboratively build a large project like this is very powerful. Very few companies in the world could launch and sustain a project that's as large as OpenStack is today. And I would argue that having, the last I saw, there were over 30,000 members of the OpenStack Foundation contributing toward the betterment of the software is a great thing.
So it is this open source infrastructure as a service operating system. Could you talk about an example of a company that uses OpenStack today so we perhaps have a prototypical use case that we can maybe refer back to during this show if we need to?
Yeah, there are several, and when I say several, hundreds of companies that are using OpenStack today in one form or another. A couple that are kind of poster children, I would say. One on the commercial side is Walmart. Walmart is using OpenStack inside their data centers as they build out their e-commerce systems. The other one is CERN, the research laboratory. that does the large scale collider over in Switzerland. And for anybody who's been to any of the recent OpenStack design summits, both of these companies have come forward and talked about their use cases and demonstrated how they're doing large-scale deployments of OpenStack.
Are these organizations, are they run by people that so they have their own servers and they run OpenStack on top of it, or are they leasing cloud hosting that they put OpenStack on?
It's a great question. And the answer is, depending upon the organization, they may do either of those or both. So the kind of typical installation when you think of OpenStack is an on-premises cloud, right? So a private cloud, if you will. So I have my own data center, and I'm probably in virtualized, right? So over the last 10 years or so, I've virtualized using VMware or other virtualization technologies. And I really want to provide, more service, more automation, and more responsiveness to my customers, my internal customers. So cloud really is an automation layer over the top of virtualization, right? So it allows me to, kind of control on-demand spin up of resources, whether they be virtual machines, storage systems, networks, etc. Right. So when you think of OpenStack, most people are looking at the use case where it's used inside of a data center. Now, it can also be, and with no change in kind of model, it can be managed by somebody else, right? So if I was a enterprise and didn't want to run my own data centers, but I contracted one of the managed hosting companies and said, please run my infrastructure on my hardware networks and so on, that OpenStack is also appropriate in that case. And then, of course, there are some cloud service providers that run OpenStack and are essentially competing in the the public cloud space against Amazon, Microsoft, Google, etc., running OpenStack.
So now we should get into how OpenStack works. We have a higher level perspective for some of the use cases and how it's deployed at a high level. You mentioned the term virtualization. What is virtualization?
Well, back in the old days, you used to buy a computer and you would put an operating system on it, and then you would run one or many applications on that operating system. About 15 years ago or so, this idea of virtualizing the servers, which really grew out of techniques that have been around for a long time in the mainframe and mini computer worlds, was brought to kind of PC level servers. And the idea behind virtualization is I can take a single computer, I can put a hypervisor on it, and what the hypervisor does is it abstracts the underlying hardware, and then it presents the ability to run multiple stacks of software from the operating system up independently. So essentially, I could take my one physical computer and make it look like 2 or 4 or 8 virtual computers. And if I'm a user of those computers, they don't look any different than if I was talking to a box that I could physically touch.
So what is the relationship, in a little more detail, what is the relationship between the hypervisor and the hardware that it sits on top of?
Yeah, so the hypervisor is a layer of software that knows what the physical hardware looks like. He knows what I call it he. It knows it knows what the
Look, this is not a gender normative podcast.
Okay. So he or she knows what the hardware looks like underneath, whether it be the CPU, whether it be the storage system, whether it be the network, and then it essentially creates driver level endpoints that can be accessed by a variety of different virtual machines.
Okay, and just to drive home what the hypervisor is a little more, talk a little more about we talked about the or you just referred to the relationship between the hypervisor and the hardware below it. Talk a little more about the relationship between the hypervisor and the virtual machines that it manages.
Yeah, so the hypervisor allows you to spin up virtual machines, and those virtual machines look and act just like physical machines. You have drivers, virtualized drivers, that provide the same services that a physical machine would do in terms of access to the CPUs, data storage, networks, and etc. Right. So it really is a translation layer between this virtualized environment and the physical hardware, and it arbitrates requests from a variety of different virtual machines down to obviously the physical hardware.
Perfect. So now that we have an idea of hypervisors, virtual machines, the hardware that all this is sitting on top of, OpenStack takes a collection of hypervisors that are spread across a data center or across multiple data centers, and it turns this collection of hypervisors into a shared pool of resources. Why is this useful?
Well, the way you described it was very good. A cloud really is an automation layer over virtual machines, right? So if you take a look at the history of data centers in the enterprise, we started off, 20 years ago with client-server architectures, and then about 15 years ago, we had kind of the rise of virtualization, and pretty much over the last, 10 years or so, most serious computation shops have virtualized. That didn't solve the problem in terms of delivery to the organization, right? So it's still, the processes that enterprises had for, let's say, a developer requesting a virtual machine or a developer requesting a group of machines was still back in the submit a ticket, have somebody go into a console or a command line, create the resources, send it, update the ticket, send email back. And this could take, several days. About 10 years ago, Amazon started Amazon Web Services. And, the key service at the time was EC2. EC2 essentially was an automated way of getting virtual machines instantly. And this is very revolutionary. So I could take my credit card, I could swipe it, right? So obviously, so they could charge me, and then immediately I could say, I want 10 virtual machines. I want them to have this much memory, this much disk. Go, and within 3 minutes or so, those machines would be up and running, and I could use them. Inside the enterprise, it's taking longer to get to that. But what OpenStack and what cloud software does is it provides that level of automation over the top of virtualization. So it's really a manager and orchestrator of virtual machines and resources.
Okay, so that's a great description. So I think to reiterate what you just said, with this shared pool of resources, you get this big pool, and there is an interface on top of it that allows the developer to not really have to worry about what's going on when the developer says, I want to spin up some amount of compute, and I don't want to have to worry about a lot of this configuration beyond the minimum that I should have to worry about as a developer. I can just specify what I want, and this huge pool of resources will figure out under the hood what to give me in actuality, and I will get a virtualized, perfect plate of resources that I need.
That's a really good way of looking at it. As a developer, right, I used to have to, if you go back 2 generations, I used to have to go buy a physical server, unbox it, right, plug it in, put the operating system on it, put my tools on it, find a place under my desk. And then when we moved into the virtual world, all that got taken care of for me, but I still had a one-to-one relationship with the virtual machine. With cloud, I just ask for the resources that I want, and I don't care if it's on machine 1 or machine 1,000 inside of the data center. As a developer, I just want access to the resources, and so we've really abstracted away the developer having to care about a lot of the provisioning pieces.
And to put a finer point on this, the shared pool of hypervisors that is managed by OpenStack, these hypervisors can be of different types. They can be Xen or KVM or VMware or Windows Server, but the user interacts with those hypervisors through a consistent interface of OpenStack. Why is this advantageous?
Because in the real world, you don't necessarily have a homogeneous set of anything, right? You may have physical computers from a variety of different sources. You may have the original provisioning may be different. You may actually have them on different types of networks. So the real world is messy. And what OpenStack does is it provides a abstracted interface over the top of the messiness and then manages the complexity underneath it, so that as a developer or really as an operator or sysadmin of the system, I don't really need to worry about that. The system will take care of it for me.
Do OpenStack users in practice, do they tend to have a heterogeneity of these different server types like KVM and VMware and Windows Server, like all within the same cluster? When a hypervisor is sitting under this consistent layer of OpenStack along with other hypervisors, are there any particular specs that the hypervisor has to adhere to, like in terms of storage or CPU or other characteristics?
It's a good question. I don't know if it's really relevant. Yes, there's probably some minimum amount of things that you have to have, right? But if you take a look at kind of any of the modern hypervisor virtualization systems, whether it be VMware or Hyper-V or whatever it is, they are all good enough to be driven by OpenStack, and OpenStack can also drive bare metal boxes as well. So, a bare metal box essentially is a box without a hypervisor.
So to ask kind of an absurdist question, what would keep me from running OpenStack across a huge cluster of Raspberry Pis?
You absolutely could do that. And if I was going to set that system up, I would not put a hypervisor on the Pi device because it's so small. But you essentially run those as bare metal boxes. But each of those would be individually addressable compute endpoints to the OpenStack scheduler.
That's really interesting. So do you think, not to get too far off course, but do you think we could have a future where I have like a data center in my closet and it's just like things that are the size of a Raspberry Pi and I can run huge MapReduce jobs on them?
Absolutely. And if you're kind of paying attention to the hotness around Docker and containers, right? So that's really helping to drive us towards that future as well, because with containers, they're much more lightweight than virtual machines, and you can get a lot higher density inside any particular configuration. So if you for instance, if we took a Raspberry Pi device and we considered that a bare metal box, and then we stacked a whole bunch of Docker containers inside of it, think about the kind of compute power you could have there, and then cluster them out underneath an orchestrator like OpenStack.
Yeah, so this is getting pretty far removed from the nature of OpenStack discussion, but I've done a number of interviews with people where I've ended up asking the question, like, when you really start to containerize your infrastructure and you're using Docker, to what degree do we get what is the effect of the economies of scale when we can containerize our architecture with more modern technologies, whereas maybe 5 or 10 years ago we were doing virtualization? Like, do you have any, I don't know, statistics or numerical projections for how economical it actually is?
Well, I can answer that, I guess, anecdotally, right? So after I ran the engineering team at Rackspace, and that's where we founded OpenStack with NASA. I then went to Hewlett Packard and stood up a public cloud based on OpenStack. My next gig was a company called AppFog, which was a platform as a service company based on Cloud Foundry. And this is, yet another level of abstraction where for a developer, it's a wonderful environment, right? Because you just worry about the logic and the components that you want in your application, and then you push it into the system, and then all the operational pieces get taken care of for you. Under the covers of any PaaS system, they're all containerized, right? So if you take a look at OpenShift or Cloud Foundry or what have you, all of these systems are running containerized systems. At AppFog, we were taking virtual machines that we were running in a variety of different public cloud infrastructures like Amazon, Rackspace, HP, etc. And we were slicing those virtual machines up to run containers. So you could take an 8 gig virtual machine and run 8 to 10 different containers inside of that. So you get much better economics, you get much better density, right? So if you have an application that's 512 meg, you don't need to take an entire 8 gig virtual machine just to run that. You can stuff more applications into the same space. And so what we're seeing is with Docker and containerized systems, it's really an inside-out platform as a service. So Docker Inc. Basically took the containerized system inside their PaaS, and they separated it out, and they made it standalone, put an API on top of it, and have done a lot of really good things in terms of collaborative development for developers and containers. And then what we're doing is with these containerized systems, we're now having to rebuild all the stuff that made PaaSes operational, like monitoring systems and health checks and things like that. So it's a really interesting world. But the short answer to your question is that I think that you're going to get 5 to 10x better utilization, and of course that means and requires that our schedulers are more intelligent as well.
Okay, great. So we'll get into the discussion of schedulers a little bit later, but let's kind of zoom out to a little bit of a higher level. OpenStack has a set of design tenets, and the two main goals of OpenStack are scalability and elasticity. And to somebody who doesn't have a whole lot of experience with building infrastructure as a service software, scalability and elasticity, these may sound like the same thing. So what is the difference between scalability and elasticity?
That's a great question, right? So if you take the scaling question first, it really is the ability to get resources on demand, right? So let's say I build an application and I'm selling something, and I'm running and I have a certain amount of traffic to it, and then suddenly it's Christmas time, right? And all the traffic to my website goes up, 10x. I either have to have over-provisioned earlier to account for the fact that now I have 10 times the amount of traffic, or when that traffic shows up, I want to scale out, right? So I want to add resources on demand. So that's really what scaling is, and the goal, the tenet of OpenStack is to be massively scalable, right? So a OpenStack system can run hundreds of thousands of virtual machines in a cluster. Elasticity really is very similar in that you want to be able to grow your resource pools, but you also want to be able to shrink them, right? And this is actually a very key part of cloud, right? So if it was just add, that would be one thing. It would be interesting. But the fact that I can actually increase my resource pool on demand and I can shrink it on demand, right? And I can do scaling both up and down is really what we mean when we say it's elastic.
Another design tenet of OpenStack is that any feature that limits the main goals of the service, which are elasticity and scalability, any example of a feature that limits those main goals must be optional. And I think this is interesting. I think it's actually really important to have these principles laid out because it's such a massive open source project, and you need to have some sense of alignment among the team, the distributed team. But what is an example of a feature that had to be made optional within OpenStack because it potentially limited scalability or elasticity?
If you take a look at the original networking options that we had, right? So we had, kind of flat networking, and we had a variety of different modes of networking that you could choose. That was, interesting. But where networking got really interesting was when this software-defined networking kind of came into being and really spearheaded within OpenStack by Nicira, who were, they were later acquired by VMware. But so suddenly we had two different networking systems, right? And you needed, as an operator or a somebody who's actually going to deploy OpenStack, you kind of had to choose between the two of them. And if we, as a group, had a policy of saying, okay, you must now use software-defined networking versus the built-in networking modules, I think that would have really retarded adoption. But the fact that you could choose, and they were optional components, made it much easier for adoption because people could choose the architecture and the mode and the style of deployment that they were comfortable with.
So everything in OpenStack should be asynchronous according to the design tenets. Why is asynchronicity so important?
If you make things synchronous, you have contention and you get blockage, and your performance goes down. So it's all about throughput. It's all about being able to create computing systems, data centers, etc., that you can put a service level agreement on. That's particularly important for enterprise adoption. Where the enterprise IT department is making an SLA promise to the business, that there'll be only so much downtime, that there's certain performance levels that will be maintained, etc. Right? So if in fact you have synchronous places in your architecture or your workflows or your systems, that's where things are going to bog down, and that's where you kind of lose control. So it really is all about maintaining performance, uptime, and scale.
OpenStack also emphasizes the importance of a shared nothing architecture. And to somebody who doesn't really understand this term, it might sound kind of strange. Like, if you have an architecture where nothing can be shared, how do you convey information from one piece of the architecture to another? So maybe you could define the term shared nothing architecture.
Yeah, so if I have a shared architecture, I may be using a chunk of memory or a chunk of disk to maintain state. And this gets very, kind of problematic when you have virtual machines that are what are called ephemeral, right? So a virtual machine can disappear on you. It can go away at any time. So you have to architect your system such that it's okay if virtual machines go away. If in fact you're using shared state and you're dependent upon this virtual machine to maintain its view of the world and it goes away, that's a problem. The way you get around this is you use things like message buses, right? So everybody's communicating on a message bus. You can subscribe to certain events, so you see state changes and things like that. You have each virtual machine has its own view of the world, and it operates on that view independent of everybody else's view.
Could you give an example of, like, hypothetically, if OpenStack would have been foolishly designed in a way that shared state was easy to do, why would shared state be dangerous? What is an example of maybe an application level bug that could propagate from a situation with shared state?
So if we're sharing state, right, I am dependent upon the thing that's maintaining the state to be correct. All right. So let's say I'll give you a good example. When I first went to Rackspace to do the cloud engineering work, they had a compute infrastructure based upon a company that they had acquired called SliceHost, and they had built an object storage system internally, right? When they, before my time, but when they went to launch the object system, in the first week, it took a lot of traffic and it went down, and it took them several days to bring it back. The problem in the design of that object storage system was they had put a centralized database, right? So, as your storage system, you've got, many disk drives. And if you're routing all your traffic and it's a requirement that you do a synchronous call to a database for each transaction, you can see how your scale is going to be impacted. The more people that are trying to talk to the system, the more contention you're going to have on that shared resource, and the worse off you're going to be, which we found to our chagrin. Now, the good news is that we learned our lesson from that, rebuilt from scratch the object storage system, and that's the system called Swift that's in OpenStack today.
Okay, great. Let's talk about eventual consistency. OpenStack is designed with eventual consistency in mind. Could you define the term eventual consistency and describe why that term is relevant to OpenStack?
Yeah, absolutely. It's absolutely a key concept for large-scale distributed systems, right? So the idea behind this is that if you have a lot of systems, I'll take the storage system again as an example. So let's say I build out my storage system and I've got 10,000 disk drives, right? And the way that object storage systems work in some instances is by doing redundant copies, right? So I write a piece of data, it actually gets splatted across the 10,000 drives, and there's at least 3 copies, right? So if at any time a drive goes away, I know I've got 2 other good copies that I can kind of recover that from. Now, the idea though is that we have latencies in systems, and we have delays in systems, right? And so if I've got a program that's looking at a particular bit of storage, and I've got another program that might be geographically dispersed but on the other side of a replication topology in the storage system, at any point in time, they both think they're looking at file foo, but foo, for some amount of time before the replication occurs, is not the same on both sides, right? So, and that's okay, and that's the whole idea behind eventual consistency. Eventually, everything will come back and be consistent as the replication works. But we have to accept the fact that in some time windows, program A and program B will get different results querying what they think is the same storage object.
And OpenStack has some degree of tunable consistency also. Could you also explain that term and explain how the level of consistency within OpenStack can be tuned?
Yeah, this is something that was added after my time. But the tighter that you bring the consistency requirements, right? Essentially what you're trading off resiliency, right? So you could actually make a system that is entirely consistent, right? So if we take eventual consistency on one end and always consistent on the other, you can build systems that operate in either of those modes, right? With OpenStack, the original design parameters for some people were not adequate, right? And this is a great thing about open source. So as part of the project, the folks that said, you know what, I don't necessarily need this many copies, but I need them to be in tighter sync, right? I need those two programs that think they're looking at the same storage object to always get the same answer if they ask the same question. That was added in as a normal part of the open source development process.
So now that we're talking about open source, could you give me an idea of how the open source community of OpenStack works and how people collaborate with each other, how the open source progresses?
Yeah, and I love this topic. I think that open source, is a tremendous movement. I think that a lot of the innovation in how we collaboratively build software has come from projects like OpenStack, and actually the requirements that large communities of folks that are spread across many countries and cultures, across many different time zones, all collaborating on a single project has forced a lot of innovation to happen. And I'm seeing the results of that innovation come back into things like how enterprises are building software, how they're building their continuous delivery pipelines, how they integrate automation into that continuous integration, continuous delivery pipeline. So with OpenStack, we started with a base set of tooling, around version control and code reviews and test automation, right? And over the years, this has gotten very, very sophisticated. So that you have your continuous integration piece, you've got your continuous testing piece, you've got your continuous deployment pieces, and the tooling around that has actually grown up out of other open source projects like Jenkins as well. The original team that was building, kind of the tools for how we managed our source code, how we built it, how we did continuous delivery, worked for me at Rackspace, also worked for me at Hewlett-Packard, and those guys did a tremendous job for the open source community. And through that kind of collaborative effort, that's how a project like OpenStack can actually be as effective as it is. It's got a good set of tooling, a good set of processes. Everybody knows what the rules are. And if you don't play by the rules, right, then you just can't affect the community. The community says, no, thank you. We don't want people that don't play by the rules. And then there's a very high level of communication and the ability to get your voice heard, right? So these are not static, written on the tablets, come down from the mountain processes. This is a living, breathing, organic process that's always being reviewed. Anybody can make suggestions. Anybody can, join the conversation. And I think it makes better software.
And speaking of processes that make better software, testing is very important to OpenStack development. Tell me about how testing occurs, what the best practices are for some open source committer who needs to commit. He wants to commit something and he has to commit tests associated with it, and maybe some of the challenges that are associated with testing a big distributed system like OpenStack.
Yeah, it's a great topic. You, as you mentioned, you have to start off with a policy and a process set of rules that says when you check in code, you check in test with it, right? So that's just you will not pass a code review if you don't have tests. How you can actually validate is a much more interesting question, and in some ways, the distributed continuous integration process really helps here, right? So you can actually set up a mesh, and this is how the original Jenkins system was set up for OpenStack, where you kind of have a master, but then you've got these slave CI systems that can be tuned for particular scenarios, right? So for instance, at Hewlett-Packard, when we were standing up OpenStack, we had a particular data center topology, right? We obviously were using HP gear, HP networks, HP racks, etc. So what our topology looked like was not the same as anybody else's in the world, and so we wanted to. It was in our own best interest to set up a slave integration server so that with each check-in that came into trunk for OpenStack, it kicked off the continuous integration process. It would go through like the basic unit test, but then it would also then farm out the work to the slave CI servers, including ourselves, and we would run through our, the testing on our particular configuration, and then we would be able to tell, we essentially gave a vote back to the CI server saying yay or nay, right? And then, of course, it's a policy decision whether or not, if you have, certain slaves failing, whether or not that blocks, the merge with trunk or not. But that's very effective, and it also works really well inside enterprises that might have different business units or departments or such. We used it within Hewlett-Packard to actually stitch together, like the networking group and the software group and the storage group. Each of those had their own view of what was necessary to pass in the OpenStack components that they were worried about, and so we set up different CI servers that they would vote back and pass the information upstream.
Okay, we've been talking about the development of OpenStack itself, and since we're drawing to the end of the conversation, I do want to zoom out a little bit more and talk about the usage of OpenStack. So with OpenStack's abstraction of a shared pool of resources, the developer gets this set of APIs exposed that gives the developer access to compute and networking and storage. And I'd love to discuss in more detail what the experience is like for the developer once this set of APIs is exposed, and how can we leverage these APIs to build our systems?
Well, that's the whole point of this, right? The point of OpenStack isn't to build a system to be building the system, although sometimes I think we lose sight of that when you're inside the project. The point of the system is to actually create an environment so that people can write applications, right? And so, the APIs that you're talking about that get exposed, even the platform services that get exposed, are all part of the, kind of the tapestry that a developer will look at, right? So at the end of the day, the point around cloud and cloud deployments and platform as a service is all around making that developer experience more seamless and really allow the developer to worry about the logic of his system rather than, gee, have I set up the web server correctly, or what are the credentials for the database, those sorts of things.
Okay, and perhaps there's one more technical topic that we haven't really dove into, and we mentioned it earlier, is the scheduler. What is the scheduler, and why is this relevant to the topic of OpenStack?
So the scheduler is really the heart of OpenStack. It's the heart of any kind of distributed system, whether you're talking about grid or high-performance computing systems, whether you're talking about containerized systems with schedulers like Kubernetes or Mesos. What the scheduler is it's an orchestrator that says, hey, I've been asked to deploy a certain workload. Where should I put it, right? And to some degree, it's kind of like, am I going to deploy one instance? Am I going to deploy multiple instances? And if I deploy multiple instances, what are the rules for affinity and non-affinity and things like that? But it really is the heart of the compute infrastructure. The scheduler is the thing that says, here's the request for running this particular program. Where am I going to put it in the fabric? Typically there'll be a feedback loop, there'll be a monitoring loop, or call it a health check or whatever you want to call it, so that if in fact I've deployed as a scheduler, I've deployed this particular workload, I'll know if it's in trouble, if it's died, and then typically within cloud systems, all of the infrastructure is what's called immutable. So instead of trying to fix something that's broken, we'll just shoot it in the head and deploy another one. And that, remember earlier we talked about the fact that we can't count on virtual machines. They are ephemeral. You can't count on them being there all the time. And part of the reason is this, right? If in fact we have to take this one out and put another one in its place and hook it up to a load balancer, we will do that. The other kind of scenario that comes into play here is workload motion. So for instance, if I have a particular server and I need to bring that server down, the first thing that I have to do is evacuate all the virtual machines and all the applications that are running on that to other parts of the system. And what will happen is that the notification will come back to the scheduler saying, hey, I've got 27 instances of applications running here that you need to find another home for. And then the scheduler will reschedule those, which allows us then to basically shut down the virtual machines and applications on the server that's going down for maintenance or whatever.
So I'd love to close by kind of zooming out further and projecting towards the future. We've got all these different ways that we can do cloud computing at this point. We've got AWS, Azure, DigitalOcean, Rackspace, anything using OpenStack. How are these different platforms going to evolve over time, and how should developers assess this situation?
That's a really great question, right? So, what we've seen over the last few years is obviously a great expansion in some of the market leaders like Amazon and Microsoft Azure. We've seen the guys at Google do some really great work. They're starting to turn their attention toward enterprise, which is new for them. And over time, I think that what we're going to see is a couple of things. we will see, I think, continued competition amongst the big players, right? So the players like that have, cash in the bank, right? And they want to control, they want to build data centers. They want to be, in the real estate power cooling business. And so we'll see continued expansion, from Microsoft and Amazon and Apple and some of these other guys. The second thing that we're going to see is competition in the vertical cloud space. So I, as a cloud service provider, it's going to be very difficult for me to really compete in this highly competitive, price-sensitive commodity business, right? But if I bring value and if I build a cloud that is targeted at a particular vertical, whether it be government oriented, whether it be healthcare oriented, whatever allows me to provide unique value for particular segments of the market, I think that we will start seeing those verticals as well. Ultimately, I think that what happens is that all this commoditization, the APIs over the top of them, the Amazon API or the OpenStack API over Rackspace's cloud, I believe that it's going to be subsumed, right? So just like today, when I put my workload into a cloud, I don't know where it's running. I think in the future I'll be able to put a workload into the cloud fabric, and the fabric will be able to, through heuristics, algorithms, the evaluation of a lot of data, we'll be able to place a workload into an Amazon data center or a Microsoft data center or a private data center, depending upon the business policies that have been defined. So my personal view, and this is what we're working on at Atomic, is to create that world.
Yeah, that it sounds really interesting. So do you think it'll be like, so I know we're up against time, but not to ask a big question, but I'll just ask a big question. Do you think it's going to be like a polyglot cloud world where like I'm a big company and I've got my media cloud that runs on maybe Netflix data, and I've got my machine learning running on Google data center because Google is great at machine learning platform as a service, and maybe I've got storage on Amazon because Amazon is best at that. Are we going towards a polyglot cloud world?
I believe that we're going towards that world, and it'll be driven by business policies and by the features and configuration of the various clouds. So that when I say I've got this particular workload and it has these characteristics, maybe one of the characteristics is machine learning, right? The system will say, oh, I know that this should go toward Google, right, rather than Amazon. Or, this is my dev test environment. Find me the cheapest place out there. Maybe it'll end up on a DigitalOcean server someplace, right? So I do believe that is where the world's going. I'm very excited about heuristic and algorithmic automation. I think it's really the third leg on the stool, right? So I think that the three legs are traditional automation that we have today, application release automation and data center automation. And that's been going on for several years, right? It started as like runbook automation and workload automation. Now we're doing a lot of DevOps things, and Atomic plays in that space. The second leg is the cloud native automation, really coming out of the PaaS world, right? So, if you take a look at Cloud Foundry, OpenShift, Heroku, they have a really rich ecosystem around the developers, and then they have opinionated automation, right, for the operators, right? So I see that those two worlds are going to be coming together sooner rather than later. And then, of course, the third leg is that heuristic or algorithmic automation, where it's non-deterministic, it's driven by policies. You basically tell the system what you want, and the system is getting a load of data, right? Call it Internet of Things, from sensors, telemetry data from servers and networks and so on and so forth, and then is able to say, hey, for this particular workload, let's put it here, whether it be Google, or let's put it in the Cleveland, Ohio private data center that we have, depending upon the characteristics of the workload and the availability of the resources.
Okay, well, that's a great place to close off. Where can people find out more about you, John?
I would go to www.atomic.com. That's our website. And I'm also on Twitter at John-Purr.
Great. Okay, well, we'll put both of those in the show notes. John, thanks for coming on to Software Engineering Radio and giving up some of your time to talk about OpenStack. This has been great.
I've had a great time. Thanks for having me on.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more information about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can write comments on each episode on the website or write a review on iTunes. Mention or message us on Twitter at SE-Radio, or search for the Software Engineering Radio group on LinkedIn, Google+, or Facebook. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under the Creative Commons 2.5 license. Thanks again for your support.